In this section, we're going to go over the central limit theorem, but this time with proportion. And you're going to see that there's going to be a couple constraints because we're dealing with proportion. So to begin, I want to do a very simple example about what exactly is a sample proportion. Well, let's consider our population. So let's say this is our population, and let's say we have everybody in the city who owns a laptop. So let's say there's a retailer who wants to know this information. They want to know what is the proportion of, or how many people in her city owns a laptop. Like, what is the proportion? Well, it's kind of impossible to survey every single person in her city, whether or not they have a laptop. So what she does is she takes a sample of, let's say, 100. So let's say this is her sample. Let's say there's 100 people inside, 100 people. And out of those 100 people, 35 has some sort of laptop. Okay, so here the sample proportion, and we call it p hat. So this little like arrow, I guess, it's called like a hat. So p hat is 35 over 100. So this is our sample proportion, and it's doing the same thing where it's trying to estimate the population proportion. So this is p. We don't know what this is because it's kind of impossible to compute. But this p without the hat is called the population proportion. Okay, so let's say the person who owns this retail took another sample of 100 people. And let's say in this sample they had 40 of them, or p hat, 40 of them out of 100 has a laptop. And again, it's doing the same thing where like it's trying to estimate the population proportion. That's the whole goal. So the idea here is like, what if we keep doing samples over and over, and we kind of ask the same question again, like what is the frequency of these different values? And that's the whole idea of central limit theorem with proportion, and that's what we're going to talk about next. So let's go over some definition. Here, in a population, the proportion who have a certain characteristic is called the population proportion. In a simple random sample of n individual, let x be the number and the sample who have the characteristic. The sample proportion is p hat equals to x over n. And the example that I showed are, I guess x is the number of people who has a laptop out of the 100 people who was in our sample. So here 35 would have been our x, and our n will be 100 because in our sample we had a sample size of 100. X was the number in the sample who have the characteristic that we care about. So here the characteristic is the number of people who owns a laptop. So that's the idea here. So some notation that we should know is that p is the population proportion, while p hat is the sample proportion. So let's go over an example. Let's consider tossing a fair coin 5 times. Here we know that our sample size will be 5 because we're tossing it 5 times. And the proportion of time that the coin lands head will be our sample proportion. So in this case, we only care about the number of time, or the proportion that the coin lands heads. Because this coin is fair, the probability that it lands on head will be 0.5. So this gives us an idea that our population proportion is 0.5. So let's make this table, or let's consider this table. Each one of these samples is a possibility of your sample space. So here, let's consider like what happens if you flip a coin 5 times and you land all, and let's say all of them lands tails. So here, p hat is the proportion. We're dealing with proportion, and since we're dealing with the number of times the coin lands head, the proportion for this sample will be 0/5, because there are 0 heads in this sample out of the total 5 that's in our sample. So this would just be 0.0. Here we have one time that our coin lands heads out of the total 5. So the proportion here, the sample proportion, will be 1/5, which is 0.2. Here again, the number of heads that comes up is only 1 time out of the total 5. So this will be 1/5. This time we'll have 2 heads that comes up out of the total 5, so this will be 2/5. And you kind of keep going with the pattern. So this will be 0.4, 1/5, 1/5, which is 0.2, 2/5, 0.4, 2/5, 0.4, and 3/5, which is 0.6. And you kind of see that I fill in the rest of the table for you, but that's the general idea here. So then the question is, what happens if we take the mean of all these sample proportion? What will happen? So here, kind of like last time, we're going to treat this like it's our population, and we're trying to find or compute the population mean of all these sample proportion. So this is going to be equal to 0.0 plus 0.2 plus 0.2 plus 0.4. So what I'm doing is adding all these values. Plus 0.2 plus 0.4 plus dot 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 dot, like all of them, adding them together, divided by 32, because there are 32 samples. And if you actually compute this, this is going to be equal to 0.5. But 0.5 is going to be, it's the same as our population proportion. And this is going to be true in general. So here we could say that the mean of our distribution of sample proportion is the same as the mean as the population mean, which is, it's population proportion P. Sorry, there we go, which is equal to 0.5. So this is true in general. The mean of our sample proportion is equal to the population proportion, which is 0.5. And again, this is true in general, just to make things clear. So I'm gonna write that down. The mean of the sample proportion, is equal to the population proportion. All right. Next, we want to see if the standard deviation is equal to the standard deviation of our population. So let's see, what if we compute the standard deviation? So it's denoted as sigma of p hat. And I'm not going to go through the work, so I'm just going to tell you it's 0.2236. And this is actually going to be equal to the square root of 0.5 times 1 minus 0.5 divided by 5. So notice that 0.5 was our population proportion, and 5 was the total number of our sample size. So you could say that this is equal to the square root of p times 1 minus p divided by n. So this is true, again, in general. So our standard deviation of our sample proportion, p hat, is equal to the square root of the population proportion times 1 minus the population proportion all over our sample size n. And again, why is this important? Well, we computed our mean and we computed our standard deviation. So these two values are going to help us, that's right, compute our z-score. And why is z-score so important? It's because it helps us compute probabilities. In summary, we could say that let p be the sample proportion of a simple random sample of size n drawn from a population with population proportion p. The mean and standard deviation of the sampling distribution of p hat are these. So the mean of our sampling distribution p hat is just going to be equal to the population proportion p, and our standard deviation of our sampling distribution p hat is just going to be equal to the square root of p, or our population proportion, times 1 minus the population proportion divided by our sample size. So here, again, n is just our sample size, and big P, or just P, is going to be our population proportion. So let's do an example. A soft drink cup at a certain fast food restaurant have a ticket attached to them. Customer peels off the ticket, you see whether they win a prize. The proportion of tickets that are winners is 0.25. A total of n equals 70 people purchase soft drinks between noon and 1 p.m. on a certain day. So here, we're going to let p hat be the proportion that wins a prize. We want to find the mean and standard deviation of our sampling distribution p hat. So what I like to do is gather all the information that we have. We know that our population proportion p is 0.25. And our sample size is 70. So n equals 70. So now we can say that our mu of p hat is just equal to it's just going to be equal to p, which is 0.25. And our standard deviation of p hat is just going to be the square root of p times 1 minus p all over n, which is going to be equal to 0.25 times 1 minus 0.25 divided by 70. And if you put this in your calculator, this should be equal to 0.0518. So like what we did in the previous section, we could actually make our histogram using the sampling distribution of our p hat. So let's consider the example we did earlier. Here, So we want to make a probability distribution table. So here we want to know how many times our sample proportion equal to 0. So if you kind of see, this only happens 1 out of the total 32 samples. So this will be 1 over 32, which is going to be equal to roughly 0.03125. And you want to look again how many of our sample proportion will be equal to 0.2. And if you look at our table, that happens 1, 2, 3, 4, and 5. 5 times. 5 out of the total 32. Which is going to be equal to 0.15625. And you kind of do the same thing for the rest of them. So here, 0.4 comes out 10 times out of the total 32. This is 0.3125. And again, here would be 10 over 32. 0.3125. This comes out 5 over 32, which is 0.15625, and here happens 1 over 32, which is 0.03125. Cool. Now that we have our table, we can construct its histogram. So here on the x-axis, this will be our p hat, or our sample proportion, and here would be our probability, p of x. So here, 0 goes up to 0.03125, so roughly around here. And then this will be around here, because 0.2 goes up to 0.15625. Then you kind of fill in the rest of them. So this will be around here. Okay, so this will be your histogram for this probability, our probability distribution table here. So what does this kind of remind you of? Kind of reminds you of a normal curve, right? And that's important because, again, when dealing with probabilities, we have to know that our curve is approximately normal in order to, compute our z-scores and compute probabilities. But another cool thing about this is that here our sample size was equal to 5, right? So we know it was equal to 5 because they only flipped the coin 5 times. So all of our sample size is just 5. But what happens if, let's say, we increase our sample size? Let's see what happens if we increase it by, say, 50. Well, you kind of see that our little rectangle are going to be like smaller and smaller, right? So that means our curve will be smoother and smoother. So it'll be like, and then at some point it's just going to be like a normal curve. So that kind of tells us that the central limit theorem is coming into play, and that's what we're going to talk about next. Now we have the central limit theorem for a proportion. Let p hat be the sample proportion for a sample size of n and population proportion p. So you have to check that if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, the distribution of p hat is approximately normal, with mean and standard deviation of this and this, which we already know how to compute. Another thing you want to note is that if p is really close to 0 or 1, a larger sample size is needed before the distribution of p hat is close to normal. Okay, so now let's talk about some of the procedures that we have to do in order to compute these probabilities using the central limit theorem. The first thing you want to check is that you want to see if all the conditions are met. If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, if they're both satisfied, then you could continue on. If even one of them does not satisfy, then you cannot compute these probabilities. Well, you can, but you have to use a method that we haven't learned in the class yet. It's a little bit more difficult. But just for this class, if these two values do not satisfy, then we cannot compute them. Okay, so let's say these two are satisfied. Then we have to find the mean and we have to find the standard deviation. Then we have to sketch the normal curve, shade the area that we want to find, and then use table 8.2 to compute its probabilities or compute the area. And if you need a little bit of a refresher, we talked about this part in 6.1, just in case you want to review. Okay, so let's do an example that combines all of these ideas together. So according to the recent Harris poll, chocolate is the favorite ice cream flavor for 27% of Americans. If a sample of 100 Americans was taken, we want to know what is the probability that the sample proportion of those who prefer chocolate is greater than 0.30. And I'm going to circle greater because that's important. Okay. One thing I want to do, or first thing I want to do, is collect all the information that's given. We know our population proportion here is going to be this 27%, or 0.27, or 0.27. We know our sample size. Here, our sample size is 100 Americans, so n is 100. So we have all the information we need. The first step is, first we have to check whether or not we're able to compute these probabilities. So you want to check if n times p is greater than 10. So this will be equal to 100 times 0.27, which gives you 27, which it is greater than or equal to 10. So that's satisfied. But we also have to check if n times 1 minus p, if this is greater than or equal to 10. So this will be 100 times 1 minus 0.27, which is equal to 73, which is definitely greater than or equal to 10. So both of these are met. So now we can compute our probabilities. So step 2. We want to know what our mean of our p hat is, which is just the population proportion p, which is equal to 0.27. And our standard deviation is the square root of p times 1 minus p over n. If you plug in these values, this should be equal to 0.27 divided by 100, and then this will be equal to 0.044396. And it's a little note I want to say here. Actually, in this case, when we want to compute your standard deviation of p hat, it's actually kind of a good thing to have a little bit more decimal. The better. It's because when we compute our z-score, we're going to actually divide this number, and we want to make it as accurate as possible to compute our table, to use for the table. Okay, so now that we have these values, mu and sigma, we can now compute our z-score. So here, z is equal to p hat minus mu of p hat divided by sigma of p hat. And which p hat are we interested in? It's actually going to be this one right here. It's what the problem wants to know. We want to know if the probability that the sample proportion of those who prefer chocolate is greater than 0.30. So here will be 0.30 minus 0.27 divided by 0.044396. And this is equal to 0.6757. And again, since we're going to use the table, we need to round this to 2 decimal places. So we look at the second number, we look at the number to the right. If it's greater than 5 or equal to 5, you have to increase it. So this is going to be equal to 0.68. Okay, now we want to draw our normal curve. So this has a mean of 0 and standard deviation of 1. So here, the goal is that we want to find greater than 0.30. So probability of z is greater than 0.68. And this kind of gives you an idea of like which area should I be shading. Since it's pointing to the right, I should be shading area to the right of my z-score. So let's say our z is somewhere around here. So this is z equals 0.68, and we want to find the area to the right of this, because we're looking for greater than 0.30. So I'm just gonna quickly, because of time, I'm just gonna quickly compute this. It will be 1 minus the area to the left, which is 0.7517, which should be equal to 0.2483. If you're still a little bit confused about this part, you could look at section 6.1 or come to my office hours, because this is really important. We're actually going to compute a lot of area under the curve throughout the semester, or the remainings of the semester. But yeah,